Good morning, good afternoon, or good evening. It all depends on what time of day you're watching this video. My name is Ferebee, and I'm a senior at Virginia State University, psychology major, and I'm here today to explain to you the Neuron Story. Now, prior to getting into the neuron story, I want you to understand what a neuron actually is. We'll more so at least just get an image of what it looks like. This picture right here represents the perfect depiction of how a neuron actually looks. And just a little pre-introduction to our neuron story, there's something we have called the ABC network. And what that is the story of the neuron unfolding through the passage of three neurons. So let's just imagine that there are three of this image on top of each other, of the exact same image. One up here, one right here, and then one at the bottom. The first image would be called cell A, the second image cell B, and the third image cell C. So once again, let's just imagine there's three of these books stacked one directly on or on top of or in front of the other, of the exact same image, and the three of these same neurons would be labeled cell A, cell B, cell C, thus creating the ABC network. Now, without further ado, let's get into action. Let's get into the neuron story. The neuron story begins when an event takes place in cell A, where neurotransmitters are released from the axon buttons, the terminal buttons of cell A, which are the green things at the bottom, which I have shown here as well. Closer image so you can see. They're released into the synapse between cell A and cell B, and the synapse is the space that's right here between the terminal buttons and the dendrites, which are these branch-looking things located at the top of axon B. Forgive me, neuron B. And you can just see it right here. This is the space, as I said before. And the blue things are actually the neurotransmitters that are released. I made them look like T's so that you would remember T for transmitter throughout the video. So wherever you see these blue T-looking things throughout this story in this video, they're the neurotransmitters. And this, once again, is the ABC network. Once the transmitters are released, four things can happen. 1, the neurotransmitters can float away. 2, they can be taken back up into cell A through reuptake. 3, can be degraded by enzymes in interstitial fluid. Or 4, bind to the receptor molecule, then bind to the binding site of a receptor molecule. And for this video, what we're going to focus on is number 4, the binding of the neurotransmitters to the receptor molecule. So take a good look at this again, and we're going to move forward. Now, as I previously mentioned, for this video, we're going to focus on option number 4, where the neurotransmitters, which you can see right here once again, the blue T's that I told you to look out for earlier in the video, have binded to the binding site on cell B. And what happens is, at this binding site, which is actually a lipid bilayer, these two receptors actually remain closed until they make contact with the neurotransmitters. And prior to moving forward, just a little background information, the lipid bilayer, which is this entire thing right here, and just imagine it being further on both sides, separates two important fluids. One fluid on the inside of the cell and one fluid on the outside of the cell. The outside of the cell contains the interstitial fluid, which the neurotransmitters are passing through, and it also contains potassium and sodium. And the interstitial fluid is what I have up here in gray, which is on the outside of the cell, which is at the top of this paper. And I wrote out just so you can, remember it for future reference and things like that. The cytoplasm is the fluid that's located inside the cell, and it pretty much possesses the same things aside from the neurotransmitters as the interstitial fluid on the outside of the cell. So once again, I've made the cytoplasm purple. I made them two different colors so that you can kind of remember. They're not necessarily these colors, but for the sake of you understanding, I made it look like this. So the interstitial fluid is on the outside of the cell, and the cytoplasm is on the inside of the cell, separated by the lipid bilayer, which is semi-permeable. Once again, this is the lipid bilayer right here. The receptors, neurotransmitters, potassium and sodium. So now we're going to move forward. Now, just to back up and move forward at the same time, the cell, which is actually the entire neuron, is prior to the neurotransmitters entering and making contact, or making contact and then entering the cell, the cell is at rest, and its resting rate is -70 millivolts. So prior to, once again, the neurotransmitters making contact with the binding site and penetrating into the cell is at rest, and its resting rate is negative 70 millivolts. Now, once the neurotransmitters make contact with the cell, they open the binding sites. Well, once they make contact at the binding site, they open the receptors, and it allows for not only the passing of neurotransmitters, but also sodium actually enters the cell. And let's just backtrack for a second. On this first chart for the resting rate, you can see that it's pretty much flatlined. You know, it's at ease. It has no events taking place, so that's why it's flatlined. Once sodium enters the cell, it depolarizes the cell and makes it more positive, thus causing this little bump right here, bump of life as I like to call it, but it's actually called the EPSP. And the EPSP is the excitatory postsynaptic potential. And once again, that's this little bump right here that's caused by the entering of sodium in the cell. And the reason, and once again, sodium is able to enter the cell only because neurotransmitters have made contact with the receptors, and it's creating an opening for the neurotransmitters to enter, as well as for sodium to enter. Once again, thus causing the EPSP, excitatory postsynaptic potential, which causes an uprise in the resting rate of the cell. So at this point, the cell is no longer at rest; it's been woken up, and it's due to EPSP, or as we can call it, sodium entering the cell. So we're going to move on to the third chart, which is the threshold of excitation chart. And just a little background information. As you can see, it's basically showing the movement from the resting rate up until the threshold of excitation, which is at negative 65 millivolts. So here's just a little background information. Multiple EPSPs add onto each other, adding more positivity to the cell, causing the threshold of excitation at negative 75 millivolts. The name of this process is called temporal summation. Temporal summation initiates an action potential. So basically, I've listed these things in chronological order so that it's easier to remember and that, it's easier to follow and easier to understand. So as I said, step 1, the resting is negative 70 millivolts. Once sodium enters the cell, it causes EPSP, excitatory postsynaptic potential, which wakes the cell up to a degree, and it's no longer at resting rate. EPSP leads to action potential, the threshold of excitation, in which multiple EPSPs add onto each other, causing the threshold of excitation at negative 65 millivolts. The process is called temporal summation, and temporal summation initiates the next step, which is known as the action potential. EPSPs are created when ionotropic receptors on the dendrites of cell B are opened. So, pretty much dendrites of cell B are opened. These are the dendrites, the little branches here again. This whole thing right here is the dendritic arborization. You can actually see dendrites, which are blue right here too. They're the tree-looking things. So now that we've got this out of the way and you pretty much understand how it's starting to connect, we're going to move on to understanding the action potential, which was listed at the bottom of this page over here. And I've highlighted some of the terminology so that you all can, write it down and take notes as you view, just to help you understand a little better. So bam, let's move to action potential. Now what I have here is a pretty, I don't want to say crude, but a pretty simple drawing of the axon, the neuron. They sound a little similar, so I get them mixed up sometimes, but this is a simple drawing of the neuron, and I only drew it just so you can understand what's coming next with the action potential. Now, an important part of the action potential is actually the axon hillock, which I've made blue, and it's pretty much the important part of this whole story. So the blue piece right here is the axon hillock. It kind of looks like I want to say a Y. Well, not really in my picture. Kind of more of a thick Y, but on this picture you can see right here the axon hillock, which is red, is kind of Y-shaped, and it's kind of like the thin part, or the part that leads to the thin tube later on the neuron. So let's go step by step. The axon is actually, which once again is in blue, location of receptors that cause the threshold of excitation. It's a location of the receptors that cause the threshold of excitation. So the receptors, as we mentioned back here on this chart, that cause this threshold of excitation are located on the axon. The axon hillock collects the consummation of all small electrical potentials And these potentials that are also responsible for the threshold of excitation then cause the opening of voltage-gated channels. Now, one thing about voltage-gated channels are they look like the receptors at the binding site. The only difference is they have no neurotransmitters involved. So where you'd see this in probably a different color on another depiction of the neuron story, the only difference between the binding site with the lipid bilayer and the voltage-gated channels is that neurotransmitters are not involved. And the reason they're not involved is because none are present. So, yeah, I wrote that down here in case you just wanted to write that down. Voltage-gated channels are similar in appearance to ionotropic receptors, which are these. Ionotropic receptors, except there is nowhere for a neurotransmitter to bind simply because one is not involved. So once again, the axon hillock is pretty much where the receptors that cause the threshold of excitation are located. And yeah, and then once that happens, it causes the opening of voltage-gated channels, and then that's when we move on to the next segment of our story. Now, this is a chart representing the action potential, and actually this chart represents everything pretty much starting from this chart I showed with the resting potential from ESP to the threshold of excitation to explaining the action potential to here. So let's break it down. As we can see, circled in green at negative 70 millivolts is when the cell is at rest. So this is once again prior to neurotransmitters making a way for sodium to enter the cell. Well, later potassium, but initially sodium entering the cell, and prior to basically anything taking place. Once sodium enters the cell, it causes a summation, which is circled in blue. So pretty much a type of excitement not to be confused with excitation, but a type of livening to the cell, waking it up pretty much. It's no longer at rest at this point once sodium enters the cell due to the positive charge. After that, the threshold of excitation occurs, and once that happens, once the threshold of excitation occurs, there's a major influx of sodium into the cell. So as you can see, the chart rises because at this point right here, sodium has entered the cell so much that it brought with it so many positive charges. And at this point, actually at the top, at the pinnacle of this chart, where sodium is, has excited the cell and has caused so much positive charge, sodium reaches equilibrium. And then once sodium reaches equilibrium, potassium gates open. Now you remember a couple of minutes back when I showed you over here that sodium and potassium are located outside of the cell. So basically what happens is so much sodium has poured into the cell that it's opened channels basically channels for potassium to also enter the cell. Now keep in mind, this is important, both are positive charges. So with that being said, the positive charges, because there's so many positive charges of sodium in the cell and now potassium, they begin to repel each other. And this actually causes the major repelling causes potassium to leave the cell, causing a hyperpolarization of the cell, which is basically a drop. So after it's excited, after sodium reaches equilibrium and the cell is at its peak, it drops again due to potassium entering the cell and causing hyperpolarization. And depolarization, earlier mentioned, is when sodium. Depolarization is the massive influx of sodium into the cell. Hyperpolarization is the cell returning, going back down or falling back to its original lower level, and ultimately, once again, reaching its resting potential, going back to where it started, pretty much. So as you can see, as I previously mentioned, potassium attempts to reach its equilibrium point of negative 75 millivolts. When it does, the cell's protein, sodium-potassium pumps, bring the cell back to rest. So, all this excitement happens. The cell is taken out of rest. Sodium enters the cell, causing a threshold of excitation. A massive influx of sodium into the cell. Potassium gates open. Potassium channels open. They pour into the cell. Sodium and potassium begin to repel each other. Potassium leaves the cell, causing the cell to drastically drop, and ultimately go back down to, or causes the cell to hyperpolarize, or hyperpolarization, ultimately going back to the resting state. Now, a thing to remember with the action potential is the all or none rule. basically meaning that action potential cannot it cannot halfway complete. It cannot kind of complete. It cannot kind of do its job. It has to completely pass through the entire axon hillock and the entire axon, ultimately to the buttons to be sent to the next cell. So the all or none rule basically means that the action potential must complete what it started and it has to do what it needs to do. So once again, I've drawn kind of like a half drawing of the neuron starting from the axon, and the orange things that you see are actually the coverings of, they're actually the coverings, well, the myelin sheath. They're the myelin sheath that covers the neuron. Located next to them are the nodes of Ranvier, as you can see, which I made the little electric volt looking things. And here's a little information about that. Each node has a potassium gated channel and a sodium gated channel, allowing both to either enter or leave the cell. Once again, the myelinated sheath. The action potential travels along the myelinated sheath or down the entire neuron. Bringing me to the definition of salutary conduction. The process by which an action potential travels down the axon hillock to completion. So it comes down the axon hillock located on the neuron, and it must come all the way down until it's completed and it's done its job to go to the next cell, which would be cell C. So now we're coming to our conclusion of the story. And I've made it simple into 3 bullet points. And here's how the story concludes. The action potential reaches the terminal button, which is the green things right here and right there, just in case you forgot. It then interacts with calcium, causing the vesicles to bind to the presynaptic membrane. Then they begin to slowly open through a process called exocytosis. Neurotransmitters spill out into the synapse between cell B and cell C. So basically, what happened in the beginning happens at the end. You know, where it started is where it will finish and where it will start again. So what I just explained here is how our story began. So the whole cycle happens again between cell B and cell C. And this has been the Neuron Story. I hope you have enjoyed, and I hope you walk away learning something. Take care.